Hey guys, how's it going? So a couple more things I want to do in chapter 28 and bring it to some closure. So I don't know, there might be a couple more parts, 2 or 3, depending on how it plays out. So the next we know that the magnetic force. We know that the magnetic force on a charged particle is given in magnitude by QVB sine of theta. The direction of the force given by the right-hand rule. Okay, we spent the last 3 or 4 parts on exploring that. So I want to point out, I'll point this out now, that in a more elegant way, the magnetic force can be written as a vector cross product. And we haven't spent a lot of time with that. We've discussed dot products, but we haven't really talked about cross products. But there's a number of you in the class that have this mathematical background. And so in a more elegant notation, the magnetic force then can be written as QV cross B, where this is a vector cross product. And for those of you who appreciate that mathematics, then you can write the force in a much more compact way, and this gives both the magnitude and the direction. Okay, beautiful. So now let's conjure up the next scenario. And so let's imagine we have a wire. So here's a wire. And I'm going to hook this wire up to a source of potential difference. This is some ideal EMF. And we know that that's going to establish a current. So there'll be a current in this circuit. And if we look at the wire in a more microscopic fashion, then we know we have mobile charge carriers moving in here of charge Q. And we know that they are moving from right to left, from left to right, with some speed. Earlier we called this the drift speed. So they're moving with some speed, velocity. If we look at direction, v. And each one of these now is going to possibly contribute to a magnetic force should this wire be placed in a magnetic field. So what we're going to do now is we're going to impose a magnetic field on this wire. So we're going to place this wire in a magnetic field, which is now oriented into the plane of the paper, screen rather, chalkboard, whatever. All right, so we have a magnetic field which is into the plane of my screen, and clearly now, right? So there will be a magnetic force, right, on each of these charged entities. The problem now is that we have a lot of them. Okay, and so the magnetic force then the magnetic force will be the sum, right? Just in words, kind of, will be the sum of the magnetic forces on all charges, moving in the magnetic field. Okay, so that's what we have in words. What's that going to look like more quantitatively? Well, let's at least do some dimensional analysis here. So in magnitude, the magnetic force then is going to be the number of mobile charge carriers, times the charge per carrier, times the speed of the carriers, times the magnitude of the magnetic field, times the sine of theta, where theta is the smallest angle between the velocity vector and the magnetic field vector. In this case, it's 90 degrees. Okay, so we will recall that the number of mobile charge carriers is given by n. Remember what this is. This is the charge carrier density, which is the number of charge carriers per volume. Okay, so then we're going to have to multiply by the volume here, so times the volume. This will be the volume times the charge per carrier. That will be Q, right? That's going to be the charge per carrier, times V, times B, times the sine of theta. So then the total magnetic force then is then going to be equal to the charge carrier density times the volume, which is going to be then the cross-sectional area. So if we go back up to this diagram, then we'll have a cross-sectional area. This is a cross-sectional area. And we will also have a relevant length of the wire in the magnetic field. I know this diagram's getting a little crazy, but all the pieces are there. So A is the cross-sectional area of that wire that's immersed in the magnetic field. L is the relevant length of that wire that's immersed in the magnetic field. And so then the volume then is going to be cross-sectional area swept through that length. Then we have the charge per unit carrier, the drift speed, the magnitude of the magnetic field, times the sine of the smallest angle between the velocity vector and the magnetic field vector. Now that's a complex equation with lots of moving parts. However, we might remember that N, A, Q times V can be bundled together. This will be L, B, sine of theta. And you might recognize this as the current. That's going to be the current times the relevant length of the wire, times B, times the sine of theta. and that's going to be the magnetic force. So let's just rewrite that out. So the magnetic force on a current carrying wire is going to be the current times L times B times the sine of theta. And this gives us now just the magnitude, right? The magnitude of the magnetic force. Magnitude of the magnetic force. Now, we need a direction, right? So we need a direction, and so that's going to require a right-hand rule, and that right-hand rule is going to be very similar to the right-hand rule for a single charge, right? So I'm gonna place my fingers. Place my fingers in the direction of the current, which is the same as placing it in the direction of the drift velocity, but on a more macroscopic scale, I'm going to place my fingers in the direction of the current. I'm going to curl my fingers such that my fingertips are in the direction of the magnetic field. And my thumb of my right hand will be in the direction of the instantaneous magnetic force. Okay, then just to redraw this picture then, we have a wire connected to a source of EMF. We're going to have a current established in this wire, so there's going to be a current. We're going to place this wire in a magnetic field. Okay, the wire is going to be of length L. The relevant length that's placed in the magnetic field. The magnitude of the magnitude of the force then, magnitude of the force is going to be ILB sine of theta. Theta is equal to the 90 degrees in this case. Doesn't need to be. Okay. And so the direction of the force on the wire then is going to be in the upward direction. So this will be FB. This will be FB. This will be FB. And so that wire will experience a net upward force given by this expression, okay, in magnitude. All right, beautiful. All right, so one more thing here. Let me just check the time. I might actually stop right here and upload this and probably have a part 6 for sure, and possibly a part 7. So anyway, thanks for tuning in. See you in a bit.